Greetings and welcome, friends. Mr. Waddy here with my geometry class in real life, friends. But you internet friends are welcome, as well as my future geometry students who will probably be listening to this. Hello from the past. We are in a new chapter, though, chapter 6. We're talking about relationships within triangles. Yeah, it's interesting. Interesting. Today we're specifically talking about perpendicular and angle bisectors, which we've actually talked about those things before, but now we've got some theorems related to them. So first of all, here's the word equidistant. A point is equidistant from two figures when the point is the same distance from each figure. Now, distance is going to be measured in the shortest way possible, which if it's the distance to a line, you'd measure it perpendicular, right? That sort of idea. So here is the PBT, perpendicular bisector theorem. Actually, I probably won't acronymize this because I feel like I wouldn't know what it was. I'd call it bisector theorem. There we go. In a plane, if a point lies on the perpendicular bisector, okay, so that's a segment, a ray, a line that happens to bisect, cut in half a segment. All right, so it passes through the midpoint, if you will, and is forming a right angle, is perpendicular to it. It claims this, that then it is equidistant from the endpoints of the segment. So it's claiming these two things are equidistant. Question, comment, observation? Yes?
Never mind.
All right, I don't mind at all. Let me show you a little sketch that I made. So here we go. I've got a segment, and the blue line is the perpendicular bisector of that segment. I've got the lengths of AB and AC, and no matter where I put this, notice that those lengths are the same, right? They're the same. How great is that? Beautiful, beautiful. We also, guess what, friends? We also have a converse of the perpendicular bisector theorem. It says in a plane. Man, best place to be. If a point is equidistant from the endpoints of a segment, so if you have a point and it happens to be the same distance from 2 points of a segment, their claim is that then it lies on the perpendicular bisector of the segment. That if you continue this, that perpendicular bisector, that was like a miss, swing and a miss. Wow. Let's see. All right. Nope. That's like all. There we go. That's even worse, but that's fine. You know what I'm saying. That it lies on the perpendicular bisector. So if if this point is equidistant from the endpoints of a segment, it happens to be on the perpendicular bisector. It's the converse. That makes sense. Let me see. Oh, there we go. So here we go. Whoa, that's crazy sauce. Look at that. So I've got a segment. The orange line is the perpendicular bisector. And notice if I move this, those two blue segments are always going to be congruent because these are congruent circles. So you can imagine a swipe and a swipe with a compass of the same radius. And wherever I go, wherever the intersection of those compass swipes are, because these are always going to be congruent, that point seems to always land on that perpendicular bisector. All right, obviously I can make it too small, but there we go. Thing of beauty. Thing of beauty. Let's see. I think I'm just going to jump right into example uno, friends. Example uno. So scrolling down. These are pretty straightforward to apply for the most part. Here we go. Oh, there we go. Using the perpendicular bisectors theorem, it says find each measure. So find RS. So RS is this guy right here. Look at this. Point S appears to be on the perpendicular bisector of RP. Therefore, it is equidistant from those endpoints, and those segments will be congruent, and therefore their measures by def of Kong will be equal. Guys, I'm done thinking that RS is 6.8. How tough was that? Right? Not that bad. Not that bad. All right, how about this? How about EG? EG on this? Okay. Here we go. All right. Here, I have a point that is the same distance from two endpoints of a segment. All right, these are the same. Therefore, this point is on the perpendicular bisector of segment EG. And therefore, if it's the perpendicular bisector, then these two segments are congruent because F is going to be the point where it's bisected. And therefore, this is 9.5. And if I double that, was that just 19? Seems like. Right? You guys liking this? So that was a use of the converse, technically. Let me hit part C here. I had to, couldn't fit it all in one snapshot. Here we go, part C. Ooh, mix it up with some algebra here. Okay, so let's find AD. I've got, by definition, a perpendicular bisector. Therefore, D is equidistant from both C and A. So these two segments are congruent. If the segments are congruent, then their measures are equal by def of Kong. And classic algebra, guys. Here we go. Man, how relaxing. It's good to be home, friends, isn't it? Wow. Good old algebra. Subtracting the 3x from both sides. I got the 2x equals the 14. Divide both sides by 2. Lovely. Isn't this lovely? Just x equals 7. Now that ain't the answer to my question. I wanted to know what AD was. And so let's see. AD is going to equal 5 times x, which is now 7. So that's 35. Right? Not bad. Yeah? You liking it? It's pretty easy. Oh, here we go. On your sketch, this is in black and white, so it's a little bit hard to see. What's labeled, but once you see my color sketch, it'll make more sense. It says, is there enough information to conclude that point N lies on the perpendicular bisector of KM? All right, so here's point N. Here's the K to the M. Well, I have these. L is the midpoint, but I wasn't told perpendicularity. Not given to me. I also wasn't told that these were equidistant. If these were equidistant, then I could have used the converse of the perpendicular bisector theorem. I feel like that should have just been called perpendicular bisector converse, but I don't know. Yeah, so I can't show that. Even if I showed like reflexive property, I can't even prove these triangles congruent to then prove that those two segments were congruent by say. So not enough information, friends. No, you can't make me show that. Now I'm assuming that bridge is probably gonna have some perpendicular support beams, but maybe not. Then again, maybe not. All right, let's see. Let's jump down to our next theorems. Ooh. Angle bisector. Wow. I mean, it was foreshadowed with the title of this section. You know, I wasn't so shocked here. It says angle bisector theorem. If a point lies, okay, so let's see. Perpendicular bisector is a line or ray or segment that cuts a segment in half and is perpendicular to it. Angle bisector, an angle bisector is a segment, line, ray, etc. that cuts an angle in half. So both of these sides of the angle are with the congruence of each other. Yes. So they're saying if a point lies on that angle bisector, then let's see. Then it is equidistant from the Yeah, don't do that. From the two sides of the angle. Now, the sides of the angle are the two rays that share the common vertex of the angle, like so. And if it's measured the distance to those sides, of course we would measure that distance perpendicular, right? Of course, because the shortest distance is going to be perpendicular to that. And it is claiming that it is equidistant from those two sides. Let me show you some geometers with the sketch pad. Oh, here we go. All right, so I've got an angle. All right, look at that. Beautiful angle. This ray is the angle bisector of this angle. All right, you can see that. Yeah, thing of beauty. Oh, that's funny when I make that too short. like so. And notice the orange segments have their measurements up there, and wherever I move this point, those are the same. All right, and then I can obviously break it, but because I didn't draw the edges of my angle all the way. But yeah, so no matter where I put it, this point is equidistant to the sides. Now this is a 90-degree angle here. Okay, I just want to make sure you realize that. Right. So converse of the angle bisector theorem is going to say the converse. You probably saw that coming. If a point lies on the interior of an angle, interesting, and is equidistant from both sides, then it has to lie on the angle bisector. Only way possible. So that means that D is on the angle bisector. So let's see. So here I've got an angle. I've got these two circles here going. Like so. Let's see. How did I manipulate their side? There we go. All right. So these two circles would suggest that this segment and this segment are congruent. And notice that the intersection there happens to lie on the orange angle bisector. Kind of no matter how I redraw that, it's just going to happen, right? Yeah. It's always hitting it no matter what. I can't make it stop hitting it. It's on the angle bisector. There. So the converse seems to at least visually make some sense. So let's put this to use. Oh man, good times. Right? Good times. How we feeling today? You guys are, wow, you guys are quiet.
Friday.
Yeah, it's Friday. You just we're listening to Senegal music, right? Yeah. Good times. So, using the angle bisector theorems. All right. Find each measure. All right. Find the measure of angle GFJ. GFJ. Okay. All right. Oh, they switched it up on us. They're sneaky. Now notice point J, follow the logic, is equidistant from these two sides of this angle, and J is in the interior of the angle. Right. Those distances are perpendicular to the sides of the angle. Therefore, this point is on the angle bisector. If JF or FJ is an angle bisector, that means this angle GFH is bisected by it, and these two angles are congruent. If those angles are congruent, their measures are equal. All right, I realize you could have just probably written 42 down like minutes ago, but Jack, I'm sure you realize and agree that the explanation is just so valuable. Right? Okay, how about this one? So this one was a use of the converse, by the way. I don't know if you caught that, converse. This one, finding RS. Okay, that's what I need. This one's going to be a use of the angle bisector theorem, all right? So this is an angle bisector. I know that because the angle's cut in half. This point S is on the angle bisector, and by the angle bisector's theorem, it is going to be equidistant from the sides. Notice these sides do happen to be measured perpendicular. Therefore, if those sides are congruent to each other, their measures are equal. And therefore, 6x minus 5 is equal to 5x. I put it over here because I like to, move the variables over to the bigger side. But actually, this will end up being one more step. Yeah, that's all right. Many ways to solve as long as we obey the laws of algebra. Right. So I'm going to get x equals 5. That does not answer the question. They wanted RS. RS is this. Now, I could plug it into that one or this one because those are congruent. But all right, Isaiah, you got this? RS equals 6 times 5 minus 5. 30 minus 5 is 25. That's a sad 2. There you go, 2. There you go. Right? Not that bad. How you feeling? How we feeling? We're good? We're good so far? Okay. Let's see. I think I can let's skip right to this soccer problem. Yeah, soccer players. Here we go.
Oh, this dude should shoot from B to L. Oh, I would stop that, John. No,
Okay.
B to R.
Who's this guy? Like, what's he doing? So if you shoot from B to L, aren't you like gonna put it closer to his path though?
You'll curl it outside.
Oh, B to R. Oh, and you'll arc it.
Yeah, I cover my.
Like that? I don't know. Well, anyways, it says, oh, it's too bad I've got that white line right there. That's fine. It says, the soccer's goalie position relative to the ball and the goalposts form congruent angles. How convenient. I mean, yeah, as shown. Will the goalie have to move farther to block the shot toward the right goalpost R or the left goalpost L? So he is on a point that happens to be on an angle bisector. Don't know if you noticed that. And that means he is going to be equidistant from both of those sides when measured at a right angle. By the how now? Angle bisector theorem. All right, angle bisector theorem. He is equidistant. Equidistant. Right, from BL and BR. What, I don't know, whatever. Whatever. Here we go. So, good. Equidistant. Yeah. Also, Jack was telling me that he should probably move forward to block the shot, because that would actually make a smaller cross section than this would, right? What are your guys' thoughts on that?
That's not a goalie though.
He's not a goal. All right. Do we have any goalies in here?
Yeah.
Should you move forward?
Definitely.
Right. I mean, this distance is shorter than this distance.
Because that's Emmett around you. That's Emmett what happens when you talk.
So if you step up, I mean, yeah. What if this? My thought was, what if this guy like does like a whoop 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 oh, and then like jukes around you?
Wait, what if he does
It's not your fault. Whoa.
That's why you have to
what if he's just the G, he goes like this, he goes right there.
Like outside center,
What if he curves it
around the red guy, and come back, check around the same side.
Okay. All right, guys. This right here is the toughest problem. One of my problems was I accidentally gave you the answer. So just try to follow along as best you can.
Isaiah tries to write the answer down.
Quiet, please. Here we go. All right. You actually possess all of the skills you need to do this problem right now, but I'll remind you of them perhaps. All right. It says write an equation of the perpendicular bisector of the segment with endpoints P, which is at -2, 3. So there's that. I'm still with orange. Orange is fine. That's fine. All right. And Q, 4, 0. So over 4 with the up 1. Okay. All right. Technically, no. If you follow the procedure well enough, you could do it without graphing. All right. So here's kind of the segment that I'm talking about, and I want to find what's the equation of the perpendicular bisector line is what I'm hoping for. Okay. In order to find that, I want to get the midpoint. There's two equations I'm going to need. Midpoint is equal to x1 plus x2 all over 2. It's the average of the x's and the average of the y's. I'll need midpoint. I'll also need the slope formula. Oh, actually, I'm going to need a bunch of equations. y2 minus y1 over x2 minus x1. Or you'd be able to just read the slope off the graph if you graphed it, right? Yeah. And then I will need a form of a line, either y equals mx plus b, which is slope-intercept form, or y minus y1 equals m parentheses x minus x1. I don't know if you guys know this one. Anyone remember that one? That's point slope form.
Oh wait, yeah.
That is like the Charizard to the Charmeleon when it comes to forms for equations of lines. Just so you're aware. I don't know if you knew that. So let's find the midpoint of this line. So midpoint is going to be the average of the x's. So -2 plus 4 over 2. And average of the y's, 3 plus 1 over 2. So the midpoint is going to be 2 over 2, comma 4 over 2. What's that going to be, guys? 1, comma 2. So let's plot that. Over 1 up to, oh, no, you didn't. Look at that. That doesn't look like a midpoint. Okay, that looks like.
That doesn't look like a midpoint.
Yeah. Now, in order to find a line perpendicular, okay, something like that. There we go. Look at those lines. Bam, bam, bam. Nope. There. Nope. 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 Ish. But if I want to find a line perpendicular, you need to remember the fact that the slope of our line, so here the slope of our line will be opposite reciprocal of this segment. So what is the slope of their line? So that's going to be 1 minus 3 over 4 minus a -2. That's a sad minus sign. There we go. There we go. So 1 minus 3 is negative dos. 4 plus 2 is 6. Negative 1/3. Okay, all right.
Can you explain that?
Yeah, I'll explain it 2 different ways. So I plugged this into this to find the slope.
Why did you say M? You say S for slope?
M is slope. M for like mountains, and S was already used for side length of a square. The other way you could have found it out is if you realize I go down 1 and over 3, down 1 and over 3, I would have gotten the slope negative 1/3. Or even if I didn't realize that the midpoint yet, I could have gone down 2 and over 6 and rise over run, negative 2 over 6, would have given me the same slope. Right? Isaiah, you with us? Yeah. So if that's their slope, what is a perpendicular line slope going to be?
Opposite reciprocal.
Opposite reciprocal. Flip it and change the sign. Here is our slope if I ever saw it. So I've got a slope, I've got a point, and I'm going to plug those facts into this or this and find an equation.
Wait, what about how did M1
Opposite reciprocal. So I flip it
what about
and change sign.
what about the B in the equation?
Exactly. Aha. What about the B in the equation? Where's the beef? So what I do for slope-intercept form, watch this. I'm going to plug in what I know. Guys, catch this move. This is top tricky.
Midpoint as the B.
The midpoint is not the y-intercept, though.
But you have to use the y-intercept.
That's if you use point-slope form, you're fine.
Yeah, but then.
So, all right, let me just show you. I'm going to plug this in for x. All right, this in for x, this in for y. You guys have seen this in a previous video. And 3 in for m. I'll plug in what I know and solve for what I don't. No hablamos, mis amigos. Comprende?
¿Por qué?
Shh, silencio.
Hola.
So, 2 equals
Hi.
3 parentheses. Quiet, gentlemen.
Wait. Why? Wait, where did you get the 2? Oh, why?
So what I'm doing here,
I got it.
all right, plug in x, y, and m, solve for b. Okay? If you know point-slope form, your job is actually way easier. But that's okay. We'll just do this, because this is what I think most of us are familiar with, even though it's harder. So solve for b. How do I solve for b? Minus 3 both sides, yep. And so I'm going to get b equals -1. So between my slope and my y-intercept, I can now write the equation of my line, y equals 3x minus 1. Let me show you what that looks like on the graph. 3x minus 1, y-intercept of 1 is right here. Isaiah, quiet. Up 3 over 1, up 3 over 1, up 3 over 1. Let's draw that line.
Okay, can you explain to me though why can't you use midpoint as a because that's the point.
Well, midpoint is not going to be a y-intercept. The midpoint's not the y-intercept.
Find the y-intercept from the
Go
midpoint.
down.
Oh, graphically? Oh, yeah. If you were able to do that graphically, most of the time we would use equations though, because graphs. What if it like crossed the y-axis at like 0.6289? Like you're not going to be able to like read that off the graph. Whereas solving it algebraically will give you an exact solution every time.
Okay.
So, right. So for our line, the midpoint is not going to be the y-intercept. All right, but if I know point slope form, I could have plugged it in for x1, y1, and it would have worked way better. All right, thanks for watching. Have a great day.